We've made big progress. We now know how to build a voltaic cell to generate an electrical potential that can move electrons through an external circuit. But now we need a method by which we can establish the absolute differences between various half reactions which constitute the extraction of electrons from one species and the donation of electrons to a particular cation. And in order to find a standard that's acceptable internationally, one that can be used in Cambridge, England, in Cambridge, Massachusetts, at PKU in Beijing, we have to have a technique, we have to have an electrode that can be reproduced with very high accuracy anywhere else in the world. And that particular electrode is called the standard hydrogen electrode. And this international standard has a number of characteristics. It's fed by moving hydrogen gas into a containment that has finely divided platinum as an electrode. And as that hydrogen flows over that electrode is submerged in an acidic solution. And that acidic solution contains H3O+. That is an H+ attached to a water molecule, forming H3O+. And as that hydrogen is bubbled over that platinum electrode, the inflow of electrons react with that H3O+ to form water. And in fact, we can write that. I'm going to write it in terms of H3O+ plus an electron going to hydrogen gas plus water. Now, in order to balance that, I need 2 of these, and I need 2 of those, and I need 2 electrons. So in come 2 electrons into our electrode. Those electrons are attracted by H3O+, and the result is the production of 2 water molecules and hydrogen gas. And that's why when this electrode is operating, you see these H2 bubbles coming out of the system. That's hydrogen produced at that electrode. And it turns out if the platinum is very clean and hydrogen is fed in at 1 atmosphere at 25 degrees Celsius, that constitutes the pinning point for all measurements of reduction potentials. And so our reaction then is 2H3O plus 2 electrons going to hydrogen gas phase, plus 2 water molecules which are in the liquid phase. And that is called the standard hydrogen electrode, or SHE in the jargon of electrochemistry. So now let's see what this implies. In front of us is a table that contains a large number of half reactions, and we're already acquainted with a number of them. We're very familiar with our silver plus cation attracting electrons. We're familiar with our zinc 2+, which has been trying to attract electrons, but so far unsuccessfully against what we have competed it against. We've just created a new one, which is H+, which can also be taken as H3O+, because H+ attracts water in the liquid. But we've set that equal to 0 in our reduction potential. That means that at 0.0, we've pinned the absolute scale for these reduction potentials. Now, coming back to silver, the silver cation, it has a standard reduction potential of plus 0.800. If we look at copper, copper has a standard reduction potential of plus 0.340. We also know that electrons were transferred from copper to silver. We also know that zinc 2+ loses out to copper 2+ in the battle for electrons when we connect the cathode and the anode. But we notice something immediately. Any half reaction that appears above another one in this table of standard reduction potentials means that that half reaction is the winner in the battle for electrons. And we can see it many times over. We saw it in the silver-copper case, where silver has a greater propensity to attract electrons, the silver cation, than does the copper cation. But the beautiful thing about this standard hydrogen electrode is that we can pin every single half reaction to the 0 point defined by that hydrogen reaction.